Time for a pop quiz.
Hello and happy Wednesday, everybody. Nice. Hello. Welcome on in. How are you doing? My name's Brian, and we are here for some extra office hours this week. So for those of you that don't know, usually I do some streaming Tuesdays, Thursdays, but I wanted to kind of expand out a little bit over the next couple weeks since I know people are heading into final exams, especially here at the college. So for those students that might have some final exams coming up, wanted to get some extra office hours in case you guys had some questions. Doing okay, how am I? I'm doing pretty well. Actually had a nice little meeting this morning with some other people in the math department. We were doing some hiring at the college, so we kind of started looking at some of our applicants. And yeah, just had a nice meeting with my partner in crime about the YouTube channel. So we'll start popping some YouTube stuff out here pretty shortly. So yeah, it's been a pretty productive morning so far. I have a bunch of stuff I have to do this evening, but yeah, it'll be a pretty busy day, I think. But otherwise, I'm doing very, very well. Hate how 50% of our questions seem to be I'm with you, Duan. Like, geometry is the bane of my existence, but probably I would say it's mostly because we just don't. Man, we don't do a lot of geometry. I don't remember doing a lot of geometry in high school. Like, I don't know if that's bad or good. Like, I feel like I don't use geometry a lot in my everyday life, which is probably why I'm so bad at doing geometry problems, but yeah. I hear you on that one. So this is the question we are currently working on. And Loims and I got a pretty good start on it yesterday. So it's a regular pentagon. We're covering up another regular n-gon. And we don't know how many sides the regular n-gon has. Right, it's a bit of a mystery. all we know is that angles A and B add up to 88. That's it, 88. That's all the info that we're given. And so I think we can, with a little bit of ingenuity, probably... I was thinking that we would do cases, but cases seemed pretty complicated, so I'm just going to erase kind of some of our work from yesterday and jot down some of the information that we were able to get from our discussion yesterday, so that we can kind of get off on a good footing. So the suggestion was to do the following. We connect the 2 points of intersection. So we connect the 2 points of intersection, and we have the following formula. We know that for an n-gon, the angles, how does it work? The angles are equal to, I think it's n minus 2 times 180 over n. So those are going to be our exterior angles. I shouldn't say that, our exterior, but those are going to be the angles kind of here, right? So the regular angles that are all the same size follow this formula. So for a pentagon, we should get that the angles are 108 degrees. Yeah, Duan, I'm totally with you. I love algebra type problems, and I love thinking, especially like number theory problems. I love number theory problems. And so I think from what we kind of glimpsed at the solution key yesterday, we need to put this 108 degrees up here. And if we connect those 2 points of intersection, then we can create 2 new angles called C and D. And then hopefully we can start crafting up some formulas to relate this stuff together. And Limes, you're thinking, I loved your spoiler alert. I like went in and I was like, oh, like he's actually gonna give a spoiler. And then you're like, oh, okay, there's a number inside of the set N. I thought that was pretty funny. I had a good laugh today. I probably shouldn't have looked at the spoiler too early, but. So, what do we know? What do we know? Levi, hello, my friend. How you doing? Shalom. Is that Jewish? I don't know. We need to get together and talk about some stuff. Because I have a potential interesting business partnership that I'm curious to get your opinion about. Yeah, we should go play pool again. We should go play pool again so that you can remind me how awful I am at playing pool. But yeah, let me know when you have some free time. I know you're probably pretty busy this week. Are you guys finishing up this week? He says he's not... Okay, so guys, he says he's not very good. Coming from the guy that literally has a pool table in his basement and has probably practiced, what, every day of your high school career? Well, that's because it's Harmeet, you know, like... You can't... He's got that brown energy, you know, you just can't beat that. That's true, I guess. Yeah, you are in Kelowna now. That's true. A little bit rusty on the pool front. So maybe without Harmeet there, maybe we can get like a true competition and see what we can actually do. Okay, I think there were a couple of things, but yeah, I definitely want to get together with you at some point here in the next couple of weeks. During your exam period, if you have some free time. So just let me know. Maybe shoot me a text. Let me know if you have some free time coming up. We can arrange a little get together. Okay, so what do we know here? We know that A and B is 88. So if we come over here to like this picture, we know that A plus B is 88. We know that C plus D plus 108 is 180 degrees because those three angles are three angles inside of a triangle. So, do I have a calculator? I think I have a calculator here somewhere. Let's see, what's 180 minus 108? Is that 72? 72. So we know that C plus D is equal to 72. And how does it work? So if a shape has... What do the angles add up to? So like this angle, like we should be able to add up all of these exterior, or I guess interior angles. We should be able to add up all of these angles and it should add up to something. So this has what, 1, 2, 3, 4, 5, 6 sides. So a 6-sided enclosed polygon is that going to have a specific number of degrees? That's my next question. So I think so. I think we just take n minus 2 times 180, right? Is that true? Does the n minus 2 times 180 work? So for a 6-sided shape, we take 4 times 180 degrees. Is that true? Does that sound right? 720? Okay, so Levi is saying 720. That's what my calculations say. It must come down to the number of triangles you can make or something silly like that, right? So like if I picked a dot and I just started making triangles, we can probably answer this question very quickly, right? By just forming triangles. So we have 1, 2, 3, 4 triangles. Oh, okay, so that's how we do it. So 4 triangles. So I'm happy with 720. So we have a 6-sided shape. All of the angles should add up to, Euclid, the elements, yes, proposition 32. So it's all about breaking your shape down into triangles, absolutely. So 720 should be all of the angles added up. So what does that mean? That means we take... What? Timothy, thank you very much for the follow. Much appreciated. Welcome to the Epsilon crew. And of course, if you have any questions about mathematics, feel free to throw them up into the chat. You can also do !DC. That'll get you into the Discord server if you need to post a photo of something. So A plus C plus B plus D plus 1, 2, 3, 4 plus 4 of our angles, and we know how big those angles are. So we have 4 of these. Does that make sense? Is that all we need? Because we know what C plus D is, we know what A plus B is. So we can just, we can just substitute this into the formula. We don't even need anything more than this. This is nuts. This is actually kind of nuts, isn't it? I thought it was going to be a pretty messy linear system. But I think it goes like, okay, we know what A plus B is. We know what C plus D is. So we just sub that in, right? This is 88. This is 72. So now it's just algebra. Hey, Duan, we've turned it into an algebra problem. I like that. Okay, so if we take 720 and we subtract our 88 and 72, we get 560. And we know that 4 times 180 is 720. So we should have n minus 2 times 720 over n. So these things have to be equal. So let's go n minus 2 times 720 should be 560n. Can we actually solve for n and get a whole number? That would be ridiculous. That would be nuts. So 720n minus, what's 2 times 720? 720 times 2, 1440. Will we get a whole number? 720 minus 560. 160n is 1440. Does 1440, is it divisible by 160? Tell me yes. Tell me yes, it is. Oh, there it is. What the fuck? Holy shit. Oh man, we were so close yesterday, so close. We just needed a little bit of help to get there. That's a really cool question. I can't believe it comes out to 9. Okay, so the regular polygon that we need is a 9-gon. That's gross, that's disgusting. Disgusting. But very cool. That was way simpler than dividing this up into cases, because the cases were not going anywhere. They were not helpful. Nonagon? Is that nonagon? Is that how you say a 9-gon? Nonagon? Nonagon. Snap. Good question. That was a good question. I like that a lot. Okay, time to start fresh, my friends. This one's got the little like handwritey thing on it. Could be a tough question. The one we did had the light bulb, so it's supposed to be one of the easier questions. Oh man, and we struggled with that one. So this is what? This is Euclid 2019. This is 5B? No, 6B. 6B. We're getting into the harder questions. Nonagon? Nona? Just sounds like grandma. Like my grandma's gone. Nonagon. She's gone. See you later. She went out to do some grocery shopping and never came back. Poor grandma. Okay, so in this trapezoid A, B, C, D, BC we know is parallel to AD. That's what those little markings mean. So there's these like weird little arrowy things. That just means that these two sides are parallel to each other. So AD and BC are parallel. And we know that BC is perpendicular to AB. Okay, so they give us the little 90-degree angle here to show that that is a 90-degree angle. So I suppose that also means that this will be 90 degrees since these lines are parallel to each other. So the lengths of AD, AB, and BC form a geometric sequence. What? Prove that AC is perpendicular to BD. What? Okay. Calculate the mass of the sun. Sure, okay. Why not? Sounds like a fun thing to do. What? I know. Why did they reward me with more geometry? Get out of here. What a bad reward. Give me number theory. Give me number theory or give me nothing. Okay, can we start putting some of this stuff? We need this, right? We need that AD, AB, and BC form a geometric sequence. So does that mean if we call AD x how does a wait, let's try again. How does it work? It's going to be a times r and then a times r squared. Is that how this works? So if AD is a, that's weird to say out loud. So if AD is little a, that's our starting term, then AB should be a times the common ratio, and then BC should be a times the common ratio squared. I think that's how this works. So that would get that piece in there. Oh yeah, similar triangle time. Totally, totally, right? So I guess I should probably highlight the triangles we're going to use, right? So we have this triangle here, which is a right-angled triangle, and we know the side lengths. And then we also have this triangle here, which we're also going to know the side lengths. So those side lengths, oh, okay, that's how they're... So it's two sides and the interior angle. So they have to be congruent, don't they? Okay, so we're going to properly prove this. I guess we need to do a couple things. We need to note that AB is perpendicular to AD. And then we can probably say that triangle ABD is similar to triangle ABC because we have side angle side, right? The ratios of the two sides plus the inner angle are the same. What does TR dab mean? TR dab? Oh, that's the triangle. Oh, triangle dab. Oh, sorry. I thought you wanted me to dab. Okay, so triangle DAB, yep, and triangle ABC are similar. Yep, got you. So that's a pretty easy argument, I think, to see. Yep. So it's like our sine 2 theta proof where we were stitching stuff together. Yeah. That's kind of was an interesting little paper. Okay, so if they're similar, that means that DB and AC have to, whatever the length of DB is, I guess AC is R times that length. So we know that AC should be R times as big as BD, right? Is that how this works? What is this? What is seg? I don't trust you after seg C. What is seg C? Just say it out loud quickly, that's all. So angle BDA. Oh yeah, those two angles, our angles have to be the same. Yeah, that's true. So yeah, let's write down a couple things. So yeah, so we know that should be true. We know that angle, what is it? ADB should be equal to angle BAC. Is that how that works? So which two angles are the same? We need ADB to be BAC, and we need ABD to be the same as BCA, right? those angles have to be the same, and maybe we should just maybe mark them. So this angle here should be the same as this one. And this angle here should be the same as this one. Okay, so we have a good amount of firepower. So can we start working away at the middle now? Oh, I see. So I guess you can now use the Z law. I forget what that is. So the Z law is going to imply that angle BCA should be equal to angle CAD, right? So in other words, I should be able to move this angle up here. Similarly, in the other direction too, right? This angle down here has to be a single dot. So by our Z law, we should have this, and we should have the angle, what, ADB. ADB is equal to angle DBC. So that's interesting. That means that a single dot plus a double dot must be equal to 90 degrees. Oh, so if a single dot and a double dot are 90 degrees, there you go. We have our final solution, right? That means that that angle here, DPC, for example, would have to be 90 degrees. Done. Nice. This was much easier than the other one. Okay, so this plus this equals 90 degrees. So angle BPC must equal 90 degrees. Done. Oh, okay. Give me number theory. Give me number theory or give me death. Okay. That one wasn't too bad. That one was actually pretty reasonable. I think that would be a fairly reasonable high school level question. Okay, feeling good about that one. Oh no, what is this? What is this? Number 7. What? It's called something other than the Z law. I just can't remember what it's called. Z law? Question mark? Geometry? Someone must know what is the Z theorem. Here it is, the Z theorem. No, that doesn't sound right. It's like parallel lines. Z law? Khan Academy must know what it's actually called. If Khan Academy would open on my computer. I don't want to watch a video, Khan Academy. Try again. Someone must know what I'm talking about. Alternate interior angles. Alternate interior angles is what it's called. I apologize for having to show you this in Comic Sans, but that's how I learned it as the Z law, but its alternate interior angles have to be the same if we know that the lines are parallel. There you go. Are you studying the elements now? Oh, last semester, okay. It's a good little book. I guess I should say it's a good little books. Books, plural. Okay, usually question 7 is pretty tame. It's just a little bit of knowing about inverses. So determine all real numbers x for which 2 log 2 of x minus 1 is equal to 1 minus log 2 x plus 2. This one feels like it should be fairly straightforward. I think we can just use some logarithm laws to clean this up a bit, right? And how does it work? So if we add these logarithms, it's really like multiplying. So we have something like log 2, and maybe I'll use some square brackets. X minus 1 squared, x plus 2. And then we can inverse this bad boy, right? So we can take, how does this work? 2 to the 1 should undo everything. So we need this multiplication to equal 2. Do I really want to expand this out? I'm going to get a cubic. So I wonder if there's an easier way to solve this. I mean, there are very few factors of 2. But they can be real numbers, so that's a pain in the butt. Like I could take x to be 0, and that seems like a pretty obvious solution. But are there other numbers? Maybe negative 1? There could be 3 possible solutions, right? Because we have an x cubed. I feel like those are the very obvious solutions. No, that's negative 1. Negative 2 squared is 4. That's not right. So 0 is a trivial solution. I think that's the only whole number solution. Oh, I guess that means if we expand it out, we should be able to factor out an x. Okay, let's give it a shot. What is this? X cubed plus 2x squared minus 2x squared minus 4x plus x plus 2. So those disappear. These disappear. Oh, I see. Okay, so we get x cubed minus 3x equals 0. So yeah, okay, so there's the trivial solution, and then we get x squared minus 3, really? So plus or minus root 3 works. That's very bizarre. However, do they all work in the original question? I feel like negative root 3 is probably not a good choice. So 0 is probably not a good choice either, because our first logarithm would be a log 2 of negative 1. So is root 3 going to be the only possible solution? I don't think the other ones work, do they? Because I'm looking at this. If I look at this up here, if I try to input x equals 0, that's bad. That's no bueno. And if we try to input negative root 3, that's also no bueno for our function. So I think we only have one solution. (14 times 12). 14 times 12. So we have, what, 144 plus another 24, which would be 148 plus 9? No, I lose. I lose. 160. Wow. Wow. Why is math so hard today? 144 plus 24. 168 plus 9. 177. Yes. Thank you. Oh my gosh. My brain. My poor brain. Okay, so loins, you said same answer? Sweet. Okay, so root 3. We're happy with that. We can double check this after. So let's take a look at part B. So part B says we have a function x squared minus 2x. Determine all real numbers that satisfy f of f of f of x. F of f of f of x equals 3. What? What? F of f of f of x. F of x. F of x. How do we start something like this? Do I really want to put f inside of f inside of f? That feels like, oh, that feels like it would be gross. There must be an easier way to do this. We can probably use the inverse somehow, right? This parabola. Ooh, but the parabola doesn't have a nice inverse to work with. We'd have to divide it up into 2 cases. What is its inverse, by the way? How do I do this again? So if I swap the x's and the y, and I want to solve for y, do I have to use the quadratic formula to do this? That sucks. I mean, at least it simplifies kind of nicely, like 2 plus or minus, we can pull out the 4 and we get 1 plus x. So all of the 2's will disappear, so our inverse function, if we wanted it, we would choose one or the other. 1 plus or minus 1 plus x under the root, and we don't need a denominator. So we could grab one of these inverses, and we could potentially use the inverse. Can we factor f? Sure, let's take a look at what that looks like. So if we factor f, we know that this is x and x minus 2. So if we have a factorization of f, is that helpful? That means that f of x would be x minus 2, x minus 2 minus 2. And that f of x would be x minus 2, x minus 2 minus 2, and x minus 2. Something like that. I mean, it might simplify nicely. I don't know. I don't know. What's this? This is x squared minus 2x minus 2. Does that factor? Does that factor nicely? No, I don't think so. Definitely not. But I mean, but they could be real numbers, right? We do want to find real numbers. If we were working with like integers, it could be a little bit easier because we know that they would have to be 1s or 3s, right? So I'm not sure if I'm ready to go down that rabbit hole quite yet. I kind of want to play around with the inverse a little bit first. So if we agree that we can choose one of these to be the inverse, which one makes the most sense? So x squared minus 2x has two intercepts. It has one at 0 and one at 2, so it should be something like this. Oh, that does make the inverse a little bit harder to work with too, doesn't it? So if 0 and 2 are the intersection points, that means that our vertex happens at 1. And so if we wanted to talk about an inverse, we would have to chop this function up where x is equal to 1. What does the inverse do for us? If we can kind of understand what the inverse does, we might be able to undo some of this notation, right? So for instance, I'm thinking if I can figure out what the inverse looks like, I could probably argue that f of x being 3 is actually the same thing as x is equal to f inverse of f inverse of f inverse of 3. In other words, I can kind of apply this inverse to the number 3 a couple times, and then I have one of my potential values for x. There might be 2 values here that make this work because we have the parabola, right? So I suspect that there's going to be 2 values that make it work. We're going to have one on each branch of the inverse. So maybe we just take the inverses one by one and apply them 3 times. Right, so maybe we do, branch 1, x is equal to f inverse of f inverse of f inverse of 3, where the f inverse we take is 1 plus this. Really? Does it just go back to 3? That'd be ridiculous. That'd be really funny, actually. What is f inverse of 3? We get 1 plus root 4, which is just 3. F inverse of 3 is 3. That's so weird. The other one's not going to be quite as straightforward. But this does suggest that 3 is probably an interesting point that'll make this work. The other one we want to check the secondary branch, which is if we take the inverse to be 1 minus 1 plus x, right? The other branch of the quadratic formula. Sensation, how dare you? How dare you come to this channel and tell me that pi is exactly 3? Be gone! How are you doing, buddy? Hope all is well in UK land. What's f inverse of 3 here? 1 minus root 4. So 1 minus 2 would be negative 1. So this is going to give me f inverse of negative 1. And then we'll have to apply this a couple more times. So what's f inverse of negative 1? We get 1. Uh-oh. If x is negative 1, we get 1? And f inverse of 1 is 1 minus root 2. So that might be another candidate. Pi is exactly 4 in taxicab metric? What? What is happening? What is going on? What is happening? I don't even know what that means. Yes? Is this true? Well, I know what the taxicab metric is. I've been in a taxi before. I know how much I have to pay to all of my taxicab drivers. What meters per second? That looks disgusting. Isn't meters per second just meters per second squared? Let's finish this question. Let's make sure these are the two values that we're actually looking for. And then I can deal with these crazy things that are happening in the comments. So 1. Does x equals 3 work? Is it true that f of 3, does that equal 3? Well, what is f of 3? F of 3 is 9 minus 6, which is 3. What? And then f of 3 is 3, and then f of 3 is 3. Check. Okay, so 3 works. Excellent. I like it when a plan comes together. What was our other x value? It was 1 minus root 2? Is it true that if we take f at 1 minus root 2 and we do that a couple of times, do we eventually get to the number 3? So 1 minus root 2, we need to square that. That's gross. So we need to square this and then minus 2 of them. 1 minus 2 root 2's plus 2. Minus 2 plus 2 root 2's. Those cancel, and we get 1. So f at 1. F at 1 is 1 minus 2, which is negative 1. And then do it one more time. Do we get the number 3? Negative 1 squared is 1. Minus 2 times negative 1. Check. So I think there are 2 possible solutions. 3 and 1 minus root 2. We get 1 of each of them from dealing with the 2 different branches of the inverse we get from applying the quadratic function, or the quadratic formula, sorry. Nuts. That's crazy. Okay, what is happening? Negative powers. Yeah, negative powers is a reciprocal situation. I agree. So if we have something like 3, it's weird to say like, I guess you could do like, normally we would write like, meters per second. But I guess technically if you wanted, you could say like 3 meters and then you could do like s to the -1. That's weird to do, but I guess it's possible to write it like that. And yeah, if you have meters per second, you usually kind of break this up into 2 fractions. And you say, oh, well, this is just meters per second, and then you flip and multiply the second fraction, and you get meters per second squared. So meters per second is really meters per second squared. And generally there's like a really nice pattern that we usually try to use here with negative powers, provided they're counting numbers. So like 5 squared we know is 5 times 5, right? 5 to the 1 is just itself. 5 to the 0 follows this pattern of always losing a multiplicative copy of 5. So you're always kind of losing a multiplication by 5. So the easiest way to think about it is we're always just kind of, as we move downwards in our powers, we're always dividing by a 5. So for instance, if I kind of get rid of this, and I add the next tier up, which is 5 cubed, this means 5 times 5 times 5. And if you want to move down in the chain, we need to divide by 5 to get to 5 squared. So dealing with powers is always about either multiplying to go to the higher rung of the ladder or dividing to get to the lower rung of the ladder. So the easiest way to talk about 5 to the -1 is to keep following this pattern of dividing by 5. And if we keep following that pattern of dividing by 5 to the -1 naturally has to be 1 divided by 5, or 1 over 5 is another way to write that. And you can keep going too, right? If you want to see the next one, which is -2, it would be 1 over 5 squared, because I need to divide by 5 again. So now you have 2 copies or 2 divisions by 5 in the denominator. Loins, I'm not saying that the strategy that I've used is going to work all of the time, but yeah, sometimes it's nice to be able to use inverses to your advantage here. Working with that quadratic was a little bit harder because the inverse could be one of 2 sides, right? The parabola we were working with isn't 1 to 1, so it doesn't have a naturally nice inverse. You have to kind of pick one side or the other, I guess. So that's why we get 2 different possible answers here, because you have 2 different possible branches you can choose for the inverse. So Levi, what is this? Okay, so let U and V be vectors. Taxicab metric says the distance between them is the absolute value of the difference of components. Yep, so when you approximate the circumference of a circle to get pi. Oh, I see, yeah. Okay. So if you have a circle and what is it? How does this work? Like you have to pick like here and no, we're doing the circumference, right? We're doing the circumference. We need to go all the way around the. How does this work? We pick a diameter of 1, right? So if d is equal to 1, then the circumference of your circle should be pi. But if you can't follow smooth arcs, no, that can't be right. Okay, so you start breaking it up into like little chunks, into little chonkers. So yeah, so like the distance from, you'd have to do something like this. Oh, okay, so you have to do something weird like this. So that's taxi cab metric. And so I guess you, so if you have more but I mean, as you have more and more of these approximations, wouldn't you still eventually get the circle? I mean, yeah, you don't have to, you don't use a polygon on the inside. Oh, but I guess what you're saying is these kind of look like squares. Oh, okay, so either you're eventually going to end up with a square outside or a square inside. So either pi is equal to 3 or pi is equal to 4. Okay. Is that the limit? Really? Does the limit actually end up looking something like this? Or like this? Like, does the limiting value of that approach actually give you that? See, I kind of see, like, I feel like if n increases, man, I feel like if n increases, it just looks like little steppies. Okay, so like if n increases, it just becomes like a bunch of these little things. It basically just becomes like a buzzsaw. So those never settle down and actually become pi. That's kind of crazy. That's actually kind of crazy to me. I feel like if you picked enough n's, that should settle down and actually get pretty damn close to pi. Not pi is equal to 4. As you add n, the distance doesn't change, really. Crazy. That's crazy times. So are you saying that this drawing that I have is kind of technically the same as this? Those two things are equivalent? What? What? That's crazy. That's kind of cool, though. So you can't... Huh. That's so bizarre. That's so bizarre. And it boils down to the commutativity and associativity of addition. Really? Wild. Although I guess I'm not terribly surprised, because all you're doing is you're working with just a bunch of absolute values. And yeah, I guess you could probably argue that certain sums of absolute values should be equal to certain sums of absolute values. Okay, yeah. So all of the distances, I guess all of the distances that go up this way, right? All of these like little tiny distances that are going up this way should be equal to this distance, and all of the little distances going this way should be equal to that distance. Oh, cool. That's a really cool way to think about it. I got it. I got you. Okay, I got you. That's crazy. That's really wild. But cool, it makes sense. I kind of get it now. Should we... So pi is equal to 4. Pi is 4.
Wow.
Who knew?
Wow.
Who knew that pi was equal to 4, guys? Who knew? I had no idea. I have seen the light. The Earth is flat and pi is equal to 4. Oh my gosh, can we skip 8a? I feel like I need to skip geometry for like a hot second. I feel like I'm gonna skip to 8b, and we're gonna finish. Oh, actually, we need to. I'll clip this. I feel like I need to not do geometry to finish off the stream. So this is Euclid. This is 2019. This is 8b. Let me get this one set up for us, so you guys can have a quick peek at it. And I do want to check our answers actually too, and make sure that we were kind of on the right track for our previous ones. So let's see, we have some solutions. So we got n was 9, right? N was 9, excellent. Different solution, who cares? That was a proof, so I'm happy with that. Root 3 is the only solution for 7a. That is what we got. And how did they actually solve part B? I'm really curious. So they said the equation blah is equal to f evaluated at a is 3. Okay, so that... They did end up using the quadratic formula, but they actually had values where I took x. But that's interesting. But they found, oh, is there more? There's more than, oh, interesting. So I didn't quite capture all the solutions, did I? I caught 2 of them. That's interesting. How did I miss some solutions? Oh, because of the squaring. You square it at every single step. So if you square it at every single step, does that affect? Oh, I guess so, right? I guess if you do f of f of f of x, you could have potentially 6 different solutions, right? Potentially 6 different solutions. I actually need to have a quick little break myself. So let's see, I need this, and give me just like a few seconds to take a small break, my friends. I'll be back in a hot minute. All right, we are back, and I have some actually pretty hungry puppies. So yeah, I guess that makes sense. We missed some solutions because of the fact that we're squaring some of the solutions along the way. That makes sense to me. So we didn't quite get everything that we needed for, what question was that? That was 7B? 7B? We missed some of those solutions. Darn. So let's finish by trying to get this question set up. And if we can solve it, that'd be great. But we're getting into some of the harder questions here. You might have to do a little bit of thinking about the setup and the execution for some of these questions now, so that we don't get bested by the... We always sometimes randomly get bested by the Euclid contest. So suppose that x satisfies, x is between 0 and pi over 2. Cos of 3 over 2 cos of x, that's gross, is equal to sine of 3 over 2 sine of x. Determine all possible values for sine 2x. And all of our answers are in the form a pi squared plus b pi plus c over d. Wow, what the heck? What the heck does this even mean? Well, you know what I'm going to do? I'm going to pull out my favorite tool, which is Desmos. We're going to look at... I'm curious about what this looks like. Like, what do these functions actually look like? So what did we have? We have cosine of 3 halves cos x. So this is our first function. And then we have sine of 3 halves sine x. Wow, they look so different from each other. Weird. So the x values that we're allowed to pick are the x values where these things intersect. Which are, I think, at just very bizarre, not friendly points. Because my instinct is to start by doing... My instinct is to think about... Oh, but they're not the same angle, are they? My instinct is to think this way. Like, where is cosine of theta equal to sine of theta? But they're not even the same theta, are they? Because it's cosine of cos x and sine of sine x. What the heck? How do you even start a question like this? I mean, we could try to apply inverse functions, but I don't think that's going to be really helpful. I guess we could start with sine of 2x is sine of 2x is 2 sine x cos x, right? So can we use that to our advantage? That's what I was wondering at first too, Loims, because I know that sine and cosine are equal when it's pi over 4, right, as our angles, but I guess, right? I guess pi over 4 is going to be a trivial solution, probably. But I think that's true though, right? Like if we look at cosine of some value and sine of some value, they're only ever equal at pi over 4. At least in the world we're working in, right? Which is between 0 to pi by 2. So I guess what we probably want... 3 halves cos x to be equal to 3 halves sine of x? But that doesn't make any sense. Because if we go back and we look at the original problem, which is, you know, if we start adding some extra stuff in here, and maybe let's put a restriction here. Maybe let's go between 0. How does this work? I think I need to do it like this. So it looks like there are 2 places where these 2 functions intersect. So we have one down here and one up here. So it's not, it doesn't feel like it's as simple as just forcing those 2 inside things to be the same. So, yeah, I think that logic doesn't make any sense. So the other thing is, could we could we square both sides? That's helpful. Yep, so certainly we could divide both sides by cosine, so we know that tan of this awful... No, that won't even work because the angles aren't the same. Right, the inside angles aren't the same, so we can't even make a tangent out of this. That's right, like we can't even do that. Right, one is 3/2 sine x and the other is 3/2 cosine x. That would be a good idea though. But yeah, we can't even do that because the angles aren't the same. So I don't know, maybe we should square both sides. Is that helpful? Yeah, so is it helpful to use the Pythagorean identity here? And I mean, we could get cosine squared of this thing plus cosine squared of this thing. We know that those 2 things have to add up to 1. But is that helpful? Is that helpful? I mean, there is a difference of squares here too, right? So that's a difference of squares, so we could factor that. Is 1/2 divided by 2 a thing? Oh, you betcha. You betcha. Suppose you have a chocolate bar. And this bit over here is half of that chocolate bar. Let's say you divide that in half because you want to split it between you and your buddy. How much do you have? Well, you have a quarter of that chocolate bar. I mean, I'd probably write it like this. Personally, it's probably how I would write it. I feel like it's weird to write it like this. Or I guess you're writing it more of like a computer science kind of way, which is something like this, right? It feels weird to write it like that, but yeah, as long as they have the brackets here, then it's obvious that you're taking the 1/2 and dividing by 2. Without the brackets, it's a little bit ambiguous what you would want. So I think if you're gonna write it like 1/2/2, you need to put the brackets there to make it make sense. It's 1/2 divided by 2. Because if you don't have the brackets there, are we doing this first? Or are we doing the 2 divided by 2 first? So yeah, I think you need a little bit of guidance in... It's very ambiguous, right? Like, this could go one of 2 ways. It could go 1/2 divided by 2, which we know is a quarter. Or if you do this step first, which is 2 divided by 2, then you'd have 1/1, which is just 1. So yeah, I think you need those brackets there to make it make sense. So there's a couple, if I was going to write it for my students, I'd probably do 1/2 with a really big bar and then divided by 2, right? So that they can see that the 1/2 is a fraction inside the numerator. Or you could write it as 1/2 divided by 2. I think that's even better. It's more clear what the expectation is. But yeah, I like it like this too. I think as long as you have the brackets there, it makes sense. 1/2 divided by 2, it's very clear what you want to do. Yeah, I think as long as you make it very clear that you have a 1/2 and you have a 2. However you do that, I think is perfectly fine in most fields. Yeah, 1/2 divided by 2. Yeah, as long as you make it clear, right, what you have. I think that's the important part, is you make it clear what you want. So is it helpful to factor this? Like if we do 1 minus cosine of the thing. It's weird that they both have a 3/2, right? Like, I almost kind of want to work with the 3/2 cos x and 3/2 sine x first. And try to find a relationship between those things. Maybe let's try that first, because if I can figure out how I can get rid of one of those things, that might be helpful. I know, I feel like I'm going back to the drawing board here, but this feels like a very odd question. So what if we had 3/2 cosine x and we had 3/2 sine x? So what do we know about these things? We know that if we, let's say take 3/2 cosine x and we square it, and we add to it 3/2 sine x and we square it. This would give us, do I even want to go that far? Yeah, probably. This would be 9/4 cosine squared x plus 9/4 sine squared x. So this would be equal to 9/4 because the cosine squared plus the sine squared would be 1. So is that enough for us to get... Maybe it's simpler than this. Maybe we just go to the triangle. No, I don't think I can make a triangle. Can I make a triangle out of this? So sine and cosine are opposite phases. Yeah, opposite in the sense that they are, yeah, they're kind of shifts of each other. Kind of opposite in this sense. I would say they're less opposite and more so a shift in how we think about things. So if I was to take cosine and move it a little bit in the rightwards direction, whoops, that doesn't happen there, it happens here. So if I was to take cosine and start moving it a little bit, then yeah, eventually they would land on top of each other. That is true. So that's kind of, yeah, so sine and cosine are related by, I think it's about 90 degrees, right? 90 degrees. So every 90 degrees they end up falling right on top of each other. That's a little hypnotizing. Slower. Well, that's nice. Yeah, they are exactly 90 degrees apart from each other. Exactly 90 degrees along the x-axis apart from each other. And yeah, Loims is correct. So the only time where these things are equal to each other is when x is pi/4 or 45 degrees. And they happen to both have the same y coordinate here. But the functions we're working with are very weird. They're very bizarre. I'm not sure how to tackle these functions. They're a little more complicated. And I guess I could start trying to think about inverse trig, but I don't really want to. Don't really want to. Because I guess I could say, I don't know what's easier to work with. Maybe like arc sine is easier to work with. I think they're both kind of suck. But I mean, they do have an inverse function on the range, or yeah, on the domain we're working with. So I could potentially take, wait a second. Which, only one of these is going to have a valid, only one of these is going to have a valid inverse function on that domain. Arc sine does not. Oh, and arc cosine doesn't either. I don't know, just for funsies, let's see. Let's see if this is helpful. I don't think it's helpful. Yeah, I don't think the inverse functions are necessarily going to be super helpful here. I'm a little stumped. Williams, yeah, thanks very much for the hangouts, and we'll see you next time for sure. I'll be back tomorrow night, hoping around 5 o'clock tomorrow night. What? Why is sine left? What mad noise? What am I looking at? We're looking at sine left x plus 4.7. Minus cosine x. That is a nice looking curve. But yeah, additions and subtractions of sines and cosines always end up looking very periodic. They look like waves, because we often use sines and cosines to model a lot of noise, right? When we're working with like music and notes and tones and things like that, sines and cosines do a very good job of modeling things like that, right? Like all the music we're listening to is all modeled by sines and cosines. It's kind of crazy. But yeah, I don't know. I'm kind of stuck on this one. I'm not exactly sure. Oh, I want to look at the solution, but I also don't want to. Okay, scroll past. I just want to see how they start this. Oh, okay. That's good to know. That's all I want to see for today. So the suggestion is that if we have cosine of x and sine of y, this implies that x plus y is equal to 90 degrees. If that's true, that's a big helpful way to move forward in this question. I don't know how that's super obvious. I'm gonna have to go and think about that a little bit, but that's the suggestion, I think, inside the solution template. I think that's the suggestion here. So I think with that said, I'm not seeing, let's see, what do I have here? I think this is just from not our particular Discord server, but yeah, if you guys do have some questions as you're starting to work towards your mathematics exams, feel free to post those questions into the Discord server under one of our little channels, right? It could be high school, it could be college level, it could be something specific like calculus, algebra, geometry, statistics, whatever you guys would like to see solutions for. Post those questions into the Discord server, and I'm happy to start working away at those this week or over the span of next week as well. So with that said, I think I'm out of here for the afternoon. I have some hungry puppies that need feeding. So you can see Shasqui having a little nap. She's our old lady. But yeah, hopefully you guys enjoyed the stream. This is a pretty tough Euclid contest. There's some pretty tricky and challenging questions here. So I'm happy to come back tomorrow. I think I'll be back around 5-ish tomorrow night. Pacific Daylight Savings Time. I think we're back to Pacific Standard Time, so PST, 5 o'clock. And yeah, we'll see if we can make some headway on some of these questions here in number 8 on the 2019 Euclid math contest. They're pretty challenging. So until then, stay positive, guys, and we will talk to you tomorrow. Take care.